Hello everybody and welcome to day 1 of booklet number 20, and we are still in 3D, and today we talk about solid shapes. And here's your art cover with the pyramids and structures and different kinds of solid shapes in them. So continuing on with our study of 3D, I'll just go into a little more detail about solids and shapes. So as usual, I always turn to the back to look at our calculations page to see what is expected of us. And so they've given us a bunch of shapes and they're telling us to name them. They're also telling us to know the faces, what is meant by faces, how many faces are there, vertices are there, edges are there in the name of these solids, right? Also, they are also asking us to do they're asking us to calculate the lateral area, surface area, and volume. And so for all of these, there's formulas, and so I guess we're just plugging in the values for R and finding out, or length, width, height, and finding out these values, right? And then I looked at their games and their the other contribution or conversation starters. Looks like they are looking at the earth and identify the 7 great circles and 2 poles, and there are games related to identifying different places on the earth and things like that, degrees and things like that. So this is really cool because this helps us to conceptualize a sphere. The earth is a sphere, and so using just that example, they've asked us to identify. So they're kind of integrating a little bit of geography into our math in this booklet. And so let's go to our charts. So as far as day 1 is concerned, everything you need to do or learn for day 1 is in this first page of the chart. So I'm going to focus more on this page for today. So let's get started, right? So we're looking at this cube sort of structure here, and let's look at these different terms because we'll be looking at these terms and these different words throughout this booklet. So I'll start with the terms. The first term is polyhedron. A polyhedron is a portion of space bounded by plane polygonal faces that formed an enclosed solid. The plural of polyhedron is polyhedra or polyhedra. Face, okay, so polyhedron is basically something or a portion of space which is bounded by plane polygonal faces. Polygonal faces are multiple faces. Just poly just means multiple, and they form an enclosed solid or a closed solid, right? For example, if I take this pen, this is a closed solid. There's multiple faces or polygonal faces, and it's enclosed, and they form an enclosed solid, right? The plural of polyhedron is polyhedra. If I had multiples of these, this marker or pen, I would call that a polyhedra, right? What is a face? The polygons that make up the sides of a polyhedron are called faces. So this is a face, right? This is a face, this is a face, and this is a face. So these are the faces, okay? What is an edge? Where the intersection of two edges, right? The edges, intersection of two faces is a segment called an edge. So this is a face and this is a face, and where do they intersect? At an edge. So this is an edge, okay? What is a vertex? The intersection of two edges is a point called a vertex. For example, you have an edge here and you have an edge here, right? Where do these two edges meet? They meet here. So that's a vertex, okay? Or you have an edge here, this is also an edge, these two edges meet over here. So this is a vertex, this is a vertex, this is a vertex, and that's a vertex, okay? All right, what's a diagonal? The diagonal is a segment which connects two non-adjacent vertices. So these two are adjacent vertices, these two are adjacent vertices. If I'm connecting this one, let me turn it around this way. If I'm connecting this edge to this edge, right? These two are not adjacent, they are diagonal, and they are not next to each other. This one and this one are not next to each other. So that is a diagonal, right? And then what's a polyhedral angle? It's a 3D angle formed by 3 or more faces or planes. So look at this angle here. This is a dihedral angle, this angle, right? Because it is formed by this plane and this plane. right in the middle of this. Okay, this is a dihedral angle. But if you look at the corner angle here, it's made by three faces. This is a face, and this is a face, and the back side is also a face. So this is a polyhedral angle. Okay, or three planes are meeting to form that angle. Okay. And then a dihedral angle, we already discussed, a 2D angle formed by two faces or planes. So in this example, this is an angle. This is an angle which is formed by this face as well as the blue thing at the bottom, right? But this one's followed by three, bounded by three spaces. This one, and the one at the back. Okay. And then base. Base is a face perpendicular to the height. So this is your base, and it's if this is your height, the height is exactly perpendicular to the base, right? In my pen example, this will be my base. This part will be the base because it is directly perpendicular to the height. Okay. What is the height? The height is the longest possible segment perpendicular to the base. So this will be my height. It is the longest possible segment which is perpendicular to the base. Okay, and the surface area is the sum of all areas of the faces. So if you take the area of this face plus the area of this face, this one, the one at the back, that pink one, the bottom one, the top one, all the faces, if you calculated the surface area or the area of all those different faces and added them together, that would be your total surface area, right? And what is volume? Volume is a measure of space contained within the solid. So for example, if this didn't have anything inside and it was hollow, how much water or liquid would it hold, right? It would hold a certain amount of volume of liquid. That is the amount, that is a measure of how much space is within the solid, right? So then I would say that is the volume of the solid. And I'm sure most of you know what volume is, but yeah. Okay, so those are the terms we'll be going across in this booklet. So let's move on to convex points. So look at this. Every vertex points outward. No plane containing a face passes through the center. Or just remember that every vertex points outward for now. Okay. And for non-convex solid, at least one plane containing a face passes through the center of the polyhedron. Example, a star polyhedra. And also you see the vertexes are not facing outward. Some of them are facing inward. Okay, so the faces pass through the center of the polyhedron. These faces are all facing outward, and like if you see, the faces are kind of pointing inward, right? And they pass through the center. Okay, so that's the difference between convex. Just remember, convex faces outward, non-convex faces inward. Okay, and then congruence between solids. So what is similarity? This little tilde mark here, that just shows that two shapes or two solids are similar if they have the same type of solid. So if you see, this is, I think, 1, 2, 3, 4, 5. It's a pentagonal kind of shape. It's got 5 sides. This is also the same exact thing. It's just smaller in size. Okay, and their corresponding radius, heights, bases, lengths, widths, etc. are proportional. So if this if the height of this solid is 10, this is 5. If the radius is 5, this is 2.5. So there's like a ratio, right? It's not just randomly that this is a certain, a bigger shape and a smaller shape. There's a ratio, and they kind of like, they maintain that ratio even if it's a smaller ratio of it. So that is similarity, right? And what is congruence? Two solids are congruent if all corresponding angles, edges, and faces are congruent, which means even the angles are the same, right? So this is exactly this has exactly the same angles as this. It has the same edges as this. It has the same faces as this. So that is when you say it's congruent. Okay, here we cannot say the angles, we cannot say that they are congruent because the edges and the faces are all different areas and things like that. But these two, that's not the case. So that's the difference between similarity and congruence. Okay, now we're moving on to classifying convex polyhedra. So let's just quickly go through these shapes. So first of all, what is a prism? I'm sure some of you have seen a prism in a science lab or something like that. It's really cool. It looks really cool. So you have two congruent parallel polygonal bases. Okay, so basically These two are exactly the same. These two bases are exactly the same. Okay, and they're connected by parallel or parallelogram sides and is named by the base. So don't worry about it. For now, just remember it looks like this. These are the lateral faces. So I have 1, 2, 3, and so similarly there'll be 3 faces at the back. 1, 2, 3. So those are my 6 lateral faces, and then I have 2 bases, one on top and one at the bottom. Okay, so this is a right hexagonal prism, and this is an oblique pentagonal prism. In a right prism, the lateral faces are perpendicular to the base. So these faces are exactly at 90 degrees angle to the base. Okay, the lateral area of right prisms, LA, short for lateral area, is the perimeter of the base. So you'll add all the sides of this base times the height. That will give you the lateral area, and the surface area will be, so basically what you're doing in lateral area, you're calculating the area of this, and the three similar faces at the back, right? So that would just be your lateral area. Surface area would be all this lateral area that you just calculated plus base, another base. So that's why they say lateral area plus 2 times the area of the base, which is these 2 bases. So surface area would be the entire thing. Lateral area would just be the area of the lateral faces. Okay, and then what else? The volume of all the prisms. So volume is basic formula, area times height, the area of the base times the height. Okay, prisms may have non-convex, non-regular polygonal bases. Okay, and there's a formula for this, but we'll come to that later. So that's about prisms. Now moving into pyramids. Pyramid has one polygonal base. Polygonal means multiple sides or multiple vertices, base, connected to one non-coplanar point by triangular sides. So you see how all the lateral faces are connecting at this point or at the apex. Okay, so that's a right hexagonal pyramid, and this is an oblique pentagonal pyramid. Don't worry about the differences. For now, just know in a right pyramid, the height from the vertex, okay, intersects the base's centroid. So the center of the base is known as the centroid, okay, in the middle of the base. So the height from here, from the vertex, will just land exactly on the centroid. That's how you identify a right pyramid. Okay, and then the lateral area is, they've given a formula, half of the base of the perimeter times height, the triangular side, or L. If this is your L, that would be what's used to calculate the lateral area. The surface area would be the lateral area plus the area of the base. Okay, and then volume of all prisms is 1/3 of this area times height. So pyramids may have non-convex, non-regular polygonal bases. So yeah, they may have non-convex bases. Yeah, just don't worry about too much about all that right now. And then what is Platonic solids? The 5 regular Platonic solids have congruent regular polygonal faces and are named for the number of faces. Okay, the first one is tetrahedron. Okay, so look at the faces. We have a solid which looks like this. This is one face. This is another face. This is the third face. Just imagine this at the back, third face, and then that's the fourth face at the back. Okay, so 2 faces at the back, 2 faces in the front, and they all meet at the apex. So the faces are 4. Let's look at the vertices. I see, oh, actually, I'm sorry, this doesn't have 2 faces here. It has 1 face here. Okay, let me think. 1, 2, 3, 4. It has 4 vertices. Because I see 4 edges. 1, 2, 3, 4, and I'm thinking, yeah, it has 4 faces too, because that's what they're saying here. So this is a face, this is a face, and then 2 faces at the back, I guess. I'm sorry, yeah, you're right. And then edges are, this is an edge, 1, 2, 3, 4. I don't know how to explain it to you. Like I need a 3D shape to show you the back of it as well. But for now, we know the edges are 6. I'll come back to this later as we work through our examples. But for now, let's keep going. We have a hexahedron or a cube. It has, why is it hexahedron? Because it has 6 faces. Hexa means 6. So 1, 2, these, I'm just looking at the bases. 1, 2, 3, 4, 5, 6, right? So 1, 2, 3, 4, 5, 6. So that would be my 6 faces. How many vertices do I have, right? So 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 vertices. How many edges do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then at the back 12, right? Like I said, I wish I had a cube or something to show you, then it would be easier to explain it to you. Maybe I can try with this. Let's see. This is an edge, that's an edge. So 1, 2, 3, 4, right? And then if I, the same 4 edges will be at the back here, right? So 5, 6, 7, 8, and then look at this, 9, 10, 11, 12. So that's 12 edges, right? So that's how we got edges is 12. Okay, and the similar things for octahedron. I guess it has 8 faces. There's a dodecahedron. There's an icosahedron. This has 20 faces. This has 12 faces. So, and they've given you how to calculate the surface area and volume for each of those shapes. The 13 semi-regular Archimedean solids have regular polygonal faces in the same arrangement at each vertex. Just forget all that. Okay, the important thing is Euler's formula for convex polyhedra. So this is the Euler's formula: vertices plus faces minus edges. So remember, vertices are your edge points, right? These points, these are your vertexes. This is your face, that's your edge. Okay, so vertices plus faces minus edge equals 2 always. Okay, this is a standard formula for you. Example, in a tetrahedron, your vertices was 4. So 4 plus 4, because your faces was also 4, minus 6 is 2. Okay, so and so if you look for everything, you'll end up with 2. Okay, all right, that's a lot of information to go over. Don't be fazed by it. Let's work through it one step at a time and we'll figure it out together. Okay, all right, so this is page 1. So you know we always do pages 1, 5, and 9 and 13 on the first day. So we're going to go with that flow, and I'm going to move this out of the way. Let me get started. Find a pencil. Yep. Okay, all right. So trace and complete. So the name of this is, from our chart, you know that this is a tetrahedron. It's got all these 4 faces and blah blah, and then you have the Euler's formula, which says faces plus vertices minus edges is 2. So they've already done the first one for you. Okay, from my chart, this looks like a, let's see, let's look at our chart. That looks like this, right? So that's an octahedron. So I'm going to write octahedron. Okay, use a pen so you can see better. So how many faces does the octahedron have? I'm just going to copy that from the chart. It has 8 faces, it has 6 vertices, and it has 12 edges. And okay, so faces plus vertices minus edges. So faces is 8, vertices is 6, minus edges is 12. So 8 plus 6 is 14, minus 12 is 2. Okay. Okay, label the parts of a regular polygon. So they're just asking you to label here, which, you know, if you look at this, if you look at your chart, on the first page itself, you have this. You have everything on that first page. So I'm just going to go ahead with that page and I'm going to label it. Okay, so where is my base, right? My base is this. I wish my camera wouldn't blur so much. But here's my base. Okay, so I'm going to write B here. Okay, and then where's my 90-degree box? I think they're talking about this. Okay, so that's my 90-degree box. So I'm just going to put this C here. What's my diagonal? This is my diagonal, so I'm going to put D there. Okay, what's my edge? This is my edge, right? Or this could also be my edge. I don't know which one they chose, but this is your edge. Okay, and then vertex. these points are your vertexes, right? So I'm going to write F here, and then what's your width? I guess this one would be your width and that would be your height, right? So G and H. Okay, and what is my length? Length would be let me look. What is this? Are they talking about this length? Let me see. Okay, they've said this is the length. Okay, so width and length are the same in a cube. Okay, but this is a rectangular polyhedron. So in a rectangular polyhedron, the longer one is your width and the shorter, this distance is your length. I guess that's new to me too. Oh sorry, that's I. Okay, and what is a dihedral angle? Remember we said when two angles intersect, so they've put a small red box here, so that's a dihedral angle, and that's J. Okay, all right. Color the lateral area and the surface area. So lateral area would be without coloring this base or this base, just this one, right? Just be the top. Like in a cylinder, it would be just the outside, right? And then these two together would be, the entire thing together would be surface area. Okay, color the liquid and compare the volume. So this liquid is a little less volume than this one, so I'm going to say this is lesser than that. Okay, verify that the Euler's formula is true. This is a hexahedron. Okay, in a hexahedron, I'm going to look at our chart and say the faces are 6, the vertices are 8. So 6 plus 8 minus 12, 14 minus 12 is, sorry, the edges are 12, so 6 plus 8, or F plus B minus E is 2. Okay. Okay, calculate using the cube's dimensions. Area of the face is length times height. Okay, so 2 times 2 is 4 inch squared. Okay, number of faces is, sorry, surface area is the number of faces times the area of the face. So basically all the faces, you just take the sum of it, or you multiply the number of faces times the area of the face, right? Which is 6s squared. So 6 times, what is our area of the face? S is 4. So 6 times 4 is 24 inch squared. Okay. Volume is side times side times side. This is all the sides are the same length, so it's going to be 8 inch cubed. Right? Okay. And then Platonic solids, they've given you these shapes which we already discussed in the chart. So the edges here are 6 in a tetrahedron. In a hexahedron, the edges are 12. In an octahedron, the edges are also 12. I'm just writing this down from the chart. Okay. Dodecahedron, the edges are 30, and icosahedron, the edges are also 30. Okay. All right, we're done with page 1. Moving on to page 5. So we have the dodecahedron. Okay, the faces, how many faces does the dodecahedron have? According to my chart, it's 12. Okay, the vertices are also 12. I'm sorry, the vertices are 20. Okay, the edges are 30. So faces is 12 plus 20 minus 30. Yep. So 12 plus 22, 12 plus 20 is 32, minus 30 is 2. Okay, icosahedron, the faces are 20, vertices are 12, the edges are 30, so this is 20 plus 12 minus 30, which is again 2. Okay, 32 minus 30. Okay, match the convex and concave shapes. So remember I said convex shapes, all the faces all point outward, right? So this one for sure looks like a convex shape. Okay, let me get another pen. Okay, and then this guy is going inward, so this is definitely not a convex, or he's rather a concave. And then the next one is this one. Let me see what they've said. Yep, that's also a concave because I guess it's going inward. Okay, and this one, everything points outward, so I'm going to say this is convex. Okay. All right, let's use we have to use these symbols to see whether it's similar or whether it's congruent. Remember, we already talked about this when we were doing the charts. Okay, so here's two line segments. It looks like just the ratios are off, but otherwise, to me, the shapes look the same. So I'm going to say it is similar. Okay. And then if I look at these two, it looks like they all have the same angle, same number of edges, vertex points, everything. So I'm going to say they are congruent. Okay. These two, this looks slightly smaller than this, so I'm going to say it's similar. Okay. And these two look exactly same. I think the angles also look pretty much the same to me, so I'm going to say they are congruent. Okay. Write the number of faces, vertices, and edges. Verify that Euler's formula is true. This is octahedron. I'm going to look at our chart, and I'm going to say, return to our chart. So in the chart, this is an octahedron. Let me see. Yep, the faces are 8, vertices are 6, and edges are 12. So 8 plus 6 minus 12 is 2. Okay, dodecahedron, same thing. 12, 20, 30, 12 plus 20 minus 30 is 2. Okay. All right. Calculate perimeter, base area, lateral area, and volume. Okay, so they've given you a shape here. Okay, and so this is 4, this is 8, that is 20. So perimeter, or the perimeter of the base is 2 times length plus width, which is 2 times of length plus width, which is 8 plus 4, which is 2 times 12, which is 24 kilometers. The area is length times width, which is 4 kilometer, times the length is 8 kilometers, I'm sorry, so it's 8 kilometer times 4 kilometer, which is 32 kilometers squared. This should be the other way around, but otherwise I'm pretty sure it's the same thing. And then the lateral area is perimeter of the base, which is 24 kilometer, times the height of the prism. What is the height? It is 20 kilometers. So 24 times 20 is 480 kilometers squared. Okay. Okay, and then the next one is volume. Volume is the area of the base, which is this one, 32 kilometers squared, into or times height is 20 kilometers. So 32 times 20 is 640 kilometer cubed. Okay, we check these values. Yep, they all look good. Okay. All right, so that completes our page 5, and I'm moving on to the next page, which is page 9. Okay. So page 9, you have the volume is side cubed for a hexahedron. So you have 6-inch cube. So 6 times 6 is 36. 36 times 6 is 18, 20, 21, 22. No, 19, 20, 21. So 216. Let me check. Yep, 216 inch squared. So I should know your cubes. If you knew your cubes table, you would have been able to say that in an instant. But unfortunately, I don't. All right. Rectangular prism. You have volume is area of base times height. Okay. So the area of the base is what's the area of this thing, right? So this is basically a rectangle. So 10 times 5 would give me the area of the base times the height. The height here is 6 inches. So this is 50 times 6 inch cubed, which is 300 inch cubed, right? All right. And then surface area is, I guess they're using a formula here, which is 2 times 5, because they're using it for the base, this base and this base, they're using this formula, plus 2 times 5 times 6, which is this one and this one, these two sides, this side and this side. These two are marked by this formula, these two sides are marked by this formula, and then what is left? This one and that one, right? So that's marked by 6 inches by 10 inches. So 2 of, or 2 times of this one, and the back one, this one. So these two sides are marked by 2 times 6 inches times 10 inches. So they've already done it for you. This is 100 inch squared, this is 60 inch squared, and that is 120 inch squared. All you have to do is just add them. So 100 plus 60 is 160. 160 plus 120 is 280, right? So 280 inch squared. Okay. All right, match the convex polyhedra. Okay, so Platonic solids. Okay, we know this is a Platonic solid. This is a Platonic solid. Okay, let's go here. Is this a Platonic? Sorry. Okay, what's a prism? This is a prism. This is a prism, right? Okay, and then what is a pyramid? That looks like a pyramid to me. That looks like a pyramid to me. And this looks like a Platonic solid to me. This also looks like a Platonic solid to me. Am I missing anything else? I don't think so. I think we got it. Okay. So where I'm getting this info is again from the chart. If you go back to your chart 1, you have all this listed there. Okay. Now circle the solids which are similar or congruent. Okay, these two, they look similar to me. They're not congruent because one is definitely smaller than the other. This one looks congruent because they look like an exact match of all the angles and edges and faces, right? Okay, is this convex or non-convex? Definitely looks like a convex because I don't see any angles or anything facing inward. This definitely looks like non-convex because I see lots of angles or faces going inward. Okay. Okay, write the number of faces, vertices, and edges. Same thing. Okay, they've not given you, they've just told you it's a cube. Okay, so how many faces does a cube have? It has 1, 2, 3, 4, 5, 6 faces, right? How many vertices does it have? It has 1, 2, 3, 4, 5, 6, 7, 8. Okay, how many edges does it have? I think we already calculated this when I used my pen example, so that it had 12 edges. So 6 plus 8 minus 12 is 2. Okay, now let's look at the octagonal prism. They've already given you the faces and edges. So you have 10 plus 16, which is 26, minus 24 is 2. Okay, calculate the basis perimeter and area, surface area, lateral area, and volume. Okay, they've already given you all of these values. You just have to plug it in and solve for it. Okay, perimeter of the base is 6 times, sorry, n, or the number, times s. So you have 1, 2, 3, 4, 5, 6. So you have 6 times s. Our s is 4 inches. So 6 times 4 is 24 inches. Okay, and then this is half of area, or half of A, which is this, times P. This is A, and times the P is the number we just calculated, which is 24. So I'm just gonna do that, and then we just multiply 12, or 3.46 times 12. Okay, 2, 6 are 12, 8, 9, sorry, 9, 6, and then you have 3, 4, 6. So you have 12, 2, 15, 11, 4. So you have 41.52. Yes. So 41.52 inch squared. Okay. And then I just have to add these, 115.2 plus 41.52, 27651, 156.72 inch squared. Okay, lateral area is half times perimeter of the base times length. Okay, so they've already given you length is 9.6, so this is 12. Again, it's 12 times 9.6. 6 2s are 12, 18, 19, and you have 96, 2, 15, 11, 115.2 inch squared. Okay, and then I'm just gonna calculate this. So you have 41.52 times 3, 6, 15, 4, 12. So that's 124.56 inch squared. Oh, sorry, inch cubed, because it's volume, right? Okay, so we're done with page 9. Moving on to page 13, the last page. Okay, you have the name is given, 6s squared. So what is our s? Our s is the length of the side, which is 4. So 6 times 4 is 24 inch squared. Okay, and then what is our volume? Our volume is length times width times height, which is 4 inch cubed. So 4 times 4 is 16. 16 times 4 is 64, I think. Yep, 64. 64 inch cubed. Okay. Okay, the name of this is a tetrahedron. Okay. They've already done this for you. 6 inch squared, square root of 3, which is 36 inch squared times square root of 3. Okay, or 36, sorry, 36 square root of 3 inch squared. Okay, I'm just moving this inch to the side. Okay, this is already done for you. So basically this is 6 inch times 6 inch times 6 inch times square root of 2 over 12. 6 will go twice and this will go 3 times. So this is 3 times 6, which is 18 square root of 2 inch cubed. Okay, I hope that was clear. I'm sorry if it wasn't, but basically I just multiplied 6 inch. Since it was cubed, I just spread it out and then I cancelled with the 12 at the bottom. Okay. All right, descriptions of regular polyhedra. Color the cross-sectional region in each cube. This one's already colored for you. Okay, and then this one, you just have to color that, this cross-section, right? So I guess you'd be coloring this part, this. Okay, that's what we're coloring. And then in a regular hex, you're just coloring a regular hexagon here, so that part. Okay, and then count the number of faces, vertices, and edges. This is a pentagonal bipyramid. Okay, they haven't given this for us, so we have to figure out the vertices. Okay, so I'm going to say that's 1 and that's 2, and then 4, 5, 6, 7. So if this has got 1, 2, 3 faces, the other side also has 1, 2, 3 faces, right? So I'm going to say 1, 2, 3, 4, 5, 6, 7, 8. Actually, they have only 7. How did they get only 7? Okay, let's see. It's a bipyramid, so maybe the backside doesn't have yeah, it's a pentagonal bipyramid. Pentagon means 5, right? So if 3 sides are represented in front, which means only two should be at the back. So if there's only 2 at the back, then there's only 1 vertex there, right? So that's 1, 1, 2, 3, 4, and 5. So this is a pentagon, this is another pentagon, so that's why it's a bipyramid. Okay, and so it's got 1, 2, 3, 4, 5, 6, 7 vertices. Okay, they're right. So 10 plus 7 minus 15, which is 2. Okay. Okay, this is a non-agonal pyramid, which I'm thinking is 9, right? So I can see already 1, 2, 3, 4, 5, 6. And how many faces can I see in front? 1, 2, 3, 4, 5, which means there's 4 faces at the back. So that's a point. So I already have 1, 2, 3, 4, 5, 6, 7, 8, 9. So, and then 10, right? Did I do that right? Let's calculate again. There's 1, 2, 3, 4, 5 faces in front. I need to have 4 faces at the back. So that's 1 face, so that's a point. That's another face, that's another point. 3, third face, and this is the 4th face. So 4 points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, 9. I get on. Oh, this one's the 10th one. Sorry. So this is 9 points, and then this should be the 10th one. Okay, so that's 10 vertices. So 10 plus, actually I needn't have calculated, they've already given it here, but I was just curious to see. Okay, calculate the base's perimeter and area. So the perimeter is number of sides times s, so 5 times s is 25 meters. The perimeter is 25 meters times 8 meters, which is the height of the prism. So that is 25 times 8 is 8 to the 16 plus 4, 200 meters squared. Okay, and then the last problem of this day is 1 by 2 times apothem. Apothem they've mentioned is 3. Okay, times 25 meter, which is our perimeter. So basically this is 3 by 2 times 25, or 75 by 2, right? Which is 37.5 meters squared. Yep. Okay, the area of the base is 37.5 meters squared times the height of the prism is 8 meters. From here, I'm getting that from there. So 37.5 times 8 is 40. 8 sevens are 48. Plus 4 is 52. 8 threes are 24. Plus 5, 29. And so I'm seeing, I'm getting, clearly did something wrong. Let me do that again. 5 eights are 40. Oh, 8 sevens are not 40. It's 56. Yep. 56 plus 4 is 60. Okay. 8 threes are 24 plus 6 is 30. Okay, so it should be 300. Sorry, meters cubed. Okay. That was a little choppy, but we got through it. Hopefully it should be smoother for us from day 2 onwards. Alright guys, I'll see you in another video. Bye.